Present video is part 2 of combinational circuits. It comes under the fourth subtopic of digital circuits as per our classifications. We'll summarize the video content here. The circuit considered here are under the headings of data transmission and data conversion, and these circuits are multiplexers, demultiplexers, decoders, encoders, and code converters. All the circuits have been explained briefly, giving a block diagram, symbol used, truth table, and they are used in circuit applications. This topic is vast, so only the limited contents are as per the needs of gate examination are covered here. So now we start the presentation, the video. The heading is the Combinational Circuits, part 2. As we said that these circuits are based on the two category of circuits. One is the circuits which come under the data transmission, that is multiplexers and demultiplexers. The other category is converters. I'll say data converters. You can write here as a data converters, and data converters we have decoders, encoders, code converters. They come under the data decoders. So we start with the topic of multiplexer. This multiplexer is also said to be data selector, and if we look into the block diagram of this circuit, we notice here there are input signals, n input signals. There are m select lines which can select the inputs to output, and there is one output line. So this is a block diagram. Input signals n, select lines m, and n equals to 2 to the power m, and there is only one output. And this circuit is also sometimes called many into one, because there are many inputs and there is only one output. So we'll take some illustrative examples of these multiplexers. Like 4:1 multiplexer, it has a 4 input, so it's a 2 to the power 2 or 2 select lines it has. 8:1 mux has 8 input, so it has 2 to the power 3 or 3 select lines. Now we see the corresponding example of 4:1 multiplexer. It's a block diagram. There are 4 inputs like D0, D1, D2, D3. S1 and S0 are the select lines, and there is one output here. The corresponding truth table for this 4:1 multiplexer is, these are data select lines and these output. Data select lines are S1 and S0. You have taken all the 4 combination of data select lines, 0, 0, 0, 1, 1, 0, and 1, 1. When it is S1 is 0, S0 is 0, we get D0 at the output. When S1 is 0 and S0 is 1, we get D1 at the output. Similarly, the other inputs. And this symbol here is and there's a symbol for multiplexer. This is a 4:1 multiplexer, so this is a corresponding symbol. There are 4 input lines and 1 output line. Instead of block diagram, presently this symbol is also quite commonly used now. You will see in gate examination question papers for multiplexer this symbol is quite common. Now from the truth table we can draw the corresponding output. Output D0 S1 bar S0 bar plus D1 S1 bar S0 bar and so on. This is a corresponding Boolean equation based on this output column. These multiplexers also have one enable input. This also sometimes called as strobe input. This signal is active low. That means the operation of the enable or strobe would be active when this pin is made low. So this is a very important signal to select a particular multiplexer, and implemented with AND gates and followed by OR gates. So obvious that the output equation could be implemented using AND gates and the corresponding OR gates. Multiplexer is also considered as the universal gate because other gates can also be derived from this multiplexer gate. Okay. Now we continue with the multiplexers further. We want to see the universality of multiplexers, so we can derive the basic gates from the multiplexer. So basic gates like AND gate, this 2:1 multiplexer. This AND gate is derived when you put 0 and A to the input of this multiplexer, and B is the select line. You get output as 0 B bar plus AB. So this is basically an AND gate. Similarly, 2:1, if you apply A and 1 to their inputs, you get A or B. But this equation, if you observe here, it's not like an equation for an OR gate, but you can notice here, as per the OR gate truth table, output is 1 when any one of the two inputs is 1, and this satisfies this equation, satisfies this equation. So basically it is an OR gate. Say NOT gate, you can generate the NOT gate by applying 1 and 0 to the inputs. Now when you want to get a high order multiplexer from the low order one, this combination is also said to be a multiplexer tree. Like 16:1 mux can be generated, can be simulated using 2 8:1 mux. Similarly, if we have 8:1 mux, it will need 2 4:1 multiplexers and OR gate. OR gate can also be replaced by a multiplexer like 2:1 multiplexer. That also you could see this, because we have seen that OR gate you can equivalently do the function of an OR. Boolean function implementation is one of the very important tasks for these multiplexers, and they can do it very nicely. This function, that means if the corresponding Boolean equation is there, or a corresponding truth table is there, you can simulate that truth table using the multiplexers. And it's just only I'm summarizing the details. You will find in the books that how it is done. Like 1 8:1 mux can implement all 3 variable logic functions. That means it can generate all the min terms corresponding to 3 variable logic function, and say sum 4 variable also. It can also do sum 4 variable logic functions by suitably connecting the multiplexer. Now the another topic is on demultiplexer. It's just inverse of multiplexer. It's also said to be a data distributor, and this circuit is said to be one into many, because in multiplexer there were more inputs and there were one output. It is the other way. There is one input here and multiple outputs are there, and there are corresponding select lines. Another name to this, we said it's a data distributor. This is a block schematic for 1:4 demultiplexer. The data input, these are the corresponding output lines, and this is the symbol for the demultiplexer. This is the corresponding truth table for the demultiplexer. These are select lines, S1 and S0, and these are corresponding output lines. You get an output, and this is the corresponding output equations, that how you get D0, S1 bar S0, D, similarly D1, D2 and D3. So very simple, and you can follow it very easily. Then another circuit is a decoder circuit. This decoder is said to be a demultiplexer without data input. There is no, if you don't have any data input, then it becomes like a decoder circuit. Here we have n inputs. This enables signal for the select of this IC, and there are less than or equal to 12 outputs. So this decoder also said to be a code converter when the number of inputs is equal to the number of outputs. Example here is BCD to XS3 decoder. Anyway, this is also, it's a 4-bit, XS3 is 4-bit. Binary to gray is also 4-bit by 4-bit, 4 to 4-bit. This is also 4-bit, 4-bit. Now IC745 BCD to decimal decoder, this is 4 to 10. That means input lines are 4, output lines are 10. 7446 are 47, and BCD is 7-segment decoder driver. That means it can drive the LED display. That's why it says it's said to be a driver. So these are some of the ICs available as a decoder. The other function is Sine Coder. Again, I'll say it's like inverse of decoder. Here you take 2 to n binary inputs, and we get an encoded outputs here. 2 to the power n to n encoder. 2 to n inputs, the enable input to the chip to the decoder, and there's n outputs. So function is inverse of the decoder. Examples are octal to binary encoder. Octal means it has 8 inputs, and binary 3 outputs. So 8 to 3 encoder. Decimal to BCD, decimal would be 10, and BCD is 4 bits. In these decoders, only one of the input line is high at a time. These decoders, only one of the input line is high at a time, and the corresponding output generated corresponding with the code. There are some circuits we call it priority encoder. In priority encoders, there could be more than one input lines could be high, and the signal with higher priority would be available at the output. So this is a priority encoder. Now the last topic is the code converter. What this code converter does? As we said, this code converter is a block diagram. This block diagram indicates that the number of inputs and number of outputs are same. And there have been enormous circuits of this application where the number of inputs is equal to the number of outputs. And convert data from one code. This input may be in one code, and you could get an output in the other code. Here as we said, the number of inputs and the outputs are same. These are some of the examples here, like BCD to binary, binary coded decimal to binary. Now binary to BCD, again binary to BCD, binary to gray, it's also 4-bit by 4-bit, gray to binary, and BCD to X3 code. All these codes are 4-bit codes, and you get both inputs and outputs. There is same number of bits, same number of, I will say, the inputs and outputs. Now one of the very important code converter is like binary to gray code. This has been very popular, and there is a good number of questions have been asked on this code converter. And here, if you see this diagram here, I'll first show you all the entire 3 diagrams which I have drawn here. These diagrams, corresponds to the Boolean equation for this code converter, and this is the logical implementation using 3 XOR gates for this converter, and this circuit here indicates that how you can convert from one particular code to the other bit by bit. Here, this input side, this is MSB and this is LSB. Here you can notice this is a binary. That's why we have said B3, B2, B1, B0, they are binary. G3, G2, G1, G0, they are the gray codes. We take B3 MSB and directly transmit to take at the output as G3. That means MSB is taken as such. And to generate G2 here, what we have done here is see, we take exclusive or XOR of B3 and B2 to generate this G2. Okay. Similarly, B2 exclusive or B1 will generate G1, and B1 exclusive or B0 will generate G0. This is the way you can generate the corresponding code. And this equation, as I said, you can see the Boolean equation, and this has been implemented in this diagram. G3 is B3, so G3 is directly coming to B3, and here G2 is B3 exclusive or B2, so this is B3 exclusive of B2 gives me G2, and G1 gives me B2 exclusive of B1, and G0 gives me B1 exclusive of B0. So we can convert this code like that. Now there is another one, the code converter, this inverse of binary to gray, this is gray to binary. Okay, so this converter, you can look at it as we have done this in the earlier case. This is here 4-bit gray code, and we have to convert from this 4-bit gray code to the binary. Okay, so how we'll look at it now? As we said earlier, there are corresponding Boolean equations for this conversion, and this is a logical implementation of this. And here we know that how this circuit or this conversion has taken place bit by bit. These are like MSB here for G3. These are gray code G3, G2, G1 and G0. This B3, B2, B1 and B0 is the binary code, and we are converting it from gray to binary. So B3 is taken as such, like G3, as per this equation. Now we can see here, to generate B2 we take B3 and exclusive OR it with G2. B3 exclusive OR with G2. This is just a direct implementation of these equations here. And here B1 is B2 exclusive OR, B2 exclusive OR G1, and B0 is B1 exclusive OR G0. So you can see this equation has been directly implemented, and this is the corresponding logical diagram for it. You should remember these conversions, because many a times there are problems and where you have to see by observation the given circuit, and by observing the circuit you can make out that what kind of circuit it is. Here the difference is because in the binary to gray code conversion, only the corresponding bits which were exclusive OR were of the same type. If it was binary, they were binary only, like you can see here, like these bits were binary only for the conversion. But in this case it is a combination of the bits of the gray and the converted bit binary, so it's exclusive OR of these two. So you can see there's some examples or some gate question paper where this conversion, gray to binary conversion question was asked. So if you notice the corresponding logical diagram or this logical equation, you can immediately guess that what kind of circuit it is. Okay, so this is end of it for this presentation. It is being observed that if we see this topic, a very good number of questions have been asked on the multiplexer part. So you can do it very thoroughly, although other topics are relatively very simple, and with less effort you can do the others also, which are there in the course, but give more stress to the multiplexer topic. Okay, best of luck. Thank you.